The meeting is recorded. Let me share my screen. So good morning, everyone. Welcome to the 5G era webinar in 2023. And this is our second year of the webinar for the project. The webinar today and tomorrow will be focused on the network applications for robotics. We will go through a few things, and then the first we'll start with the story of distributed robotics. And then we will explore the 5G era solution, the deployment model. And then after that, I will go through the agenda of the webinar, a lot of contents packed up today and tomorrow. And then I will quickly go through the future of the 5G era events. I'm not going to the technical details in my introduction over here, but I will give you the story on why do we need to have this development, what is the rationale, and what is the key innovations to be delivered. And that is kind of things we try to convey to translate our knowledge into accelerate development for you on distributed robotics. Starting with the idea of the distributed robotics, every day, everything has been connected with the world of the digitalization. Robotics is not in exception. It is expected to be a key capability of the future robotics. This movement is not purely built up by robotic community. It is unparalleled, built up by the cloud computing people and the networking community. So the synergy among different disciplines coming together eventually enable the application of the movement of distributed robotics. The key feature over here is that we are building up some sort of adaptive autonomy on delivering the frictionless integration between the deployment of the robot and the digital environment. So we hope robot is clever enough to utilize the surrounding ambient environment, surrounding digital world, to maximize its impact, to maximize its performance. That is the goal of the distributed robotics, so the robot can collaborate among each other and helping the task execution using the resource from the surrounding environment. The application scenario, there are many, many of them. The most direct scenario will be robot will be offloading the task originally running on the robot to the surrounding environment, or collaborate with the surrounding environment in terms of task execution. Like other cloud computing or networking solutions, we want this distributed robotic scenario to be on demand and to be frictionless. So this means that the developer of robot applications can directly consume the service 5G, cloud, MEC without major modification on their current routines, and they can just take it and use it. With this application scenario, what is the state of art? In terms of robot deployment, this is a very hot topic. From roughly 15 years ago, robot operating system has been dominant on the deployment of robot. Started from ROS 1. In ROS 1, you have ROS master, and you do the publisher and subscriber. You link all the topics together, and eventually you deliver the connected robotic applications for the targeted usage scenario. But obviously, you can see this is mainly based on multicast broadcasting, and which means that you are limited to a single piece of net. That means the scalability of ROS is not very good. And understand this problem, and I think probably 7 or 8 years ago, there is a new revision on ROS called ROS 2, This is significantly changed the landscape of ROS development. They introduced the idea of the DDS, which can integrate multiple subnets together using unicast, using multicast. So we will be able to have different kind of subnets glued together to deliver the targeted application. So that is pretty much the latest application of robot deployment. There are adaptations of DDS and ROS2 like DDS router, so it's different kind of fix in terms of resolving the deployment issue for the robots. I'll give you one example, which is what we have been facing recently. So this is a deployment example we had in Valencia integration meeting last year, and the robot here is Robotics Summit XL, and then we have our developer Glenn here controlling the robot. In this scenario, the robot is connected to AWS EKS service remotely. At the same time, robot is also connected to the local edge devices come from the company. AWS have their own security policy with their own restrictions on the access. The company also have their local policy for the access control. At the same time, when robot moving around and the topology of the connection is expected to be changing from time to time. Effectively, we do not have a fixed topology, and depends on the location, depends on the quality of service. Robot has to adapt itself to be connected to the right network at the right time. So that kind of scenario, we realize that even for ROS2, for DDS, it does not work. Mainly because that most of existing robot application or the deployment of the robot based on ROS is designed for structured environment. This is about the laboratory, industry environment. In those kind of environment, you have fixed quality of service, you have static network topology, you have a single domain, and you have single kind of administration restrictions. So effectively, for ROS2, for DDS, in this environment, you can control yourself. You will be able to introduce some kind of global policy to control the deployment behaviors. However, in real world settings, they are unstructured and quality of service change constantly. Network topology is dynamic. We have multiple domains coexist at the same time. We have multiple administrations with different kind of security requirement happening to the robot deployment. For this kind of real world deployment, we are still missing the right development environment. We are missing the right framework to support the robot deployment in a large scale. On the other hand, as I said, distributed robotics, the co-development between multiple disciplines. For the networking community, and there are also good application scenarios. In that direction, we want to have an orchestrated digital environment to support quality of experience for vertical. Effectively, we want to have the best experience, in our case, distributed robotics, to be delivered based on the surrounding digital environment. The target is about task-oriented resource allocation provision, scaled across different kind of domains, and then also optimized for knowledge sharing. So that is the expectations from the networking community to have their service fully delivered to the verticals. I'll give you some more example over here. So in this sense, this is the left-hand diagram is come from Hexia. This is a flagship European project on 6G vision. So they are talking about digital world connected with physical world, with connected intelligence, and then different kind of immersive communication to be delivered. It's very, very good vision for the future. However, we're facing direct hurdles for the deployment of this kind of capability. The first problem is about the transparency and task-oriented quality of experience. I give you one example here. For teleoperation, we want minimal latency. We would like to have as small latency as possible in terms of performing the remote operation. For environment perception, on the other hand, we don't really care too much about latency. We want high throughput. So the high throughput will help us to get better processing on the environment information. So it depends on the task. There are different expectations on the quality of experience. However, from the networking perspective, we want to deliver the transparency. We want to have the location. We want to have the operation transparency in terms of no matter where you access our system, you have same kind of experience. So this is kind of a dilemma faced by the development. How can we do that? And another thing is about for vertical application, in our case, robot application, we have our domain knowledge. So the resource provision, the knowledge provision from the surrounding digital world need to be optimized for our domain. So this is domain-driven design we have been focusing on. But at the same time, for networking community, the number one focus you are working on is on scalability. So there is also a contradictory requirement to deliver scalable solutions. At the same time, you have to cover the specific demand of one individual domain. So this is a lot of challenge faced by us that come to our project. And the project is called 5G Enhanced Robot Autonomy. We started from January 2021, around 6 million euro invested by the Commission to do the 5G enhanced autonomous robot within with intelligent capability to explore the digital environment. The project is coordinated by Robotics Automation SRL, and Rafa Lopez is a project coordinator. I am the scientific coordinator of this project with many partners joining the movement to deliver the innovation of the 5G enhanced autonomous robot. Our main innovation is defined in 4 categories. The first one is about reference design for 5G enhanced cloud robotics under connected intelligence. The second one is about vertical oriented orchestration for intent-based networking. The third one is about unified communication interface for large-scale distributed robot deployment. The last one is about cloud-native network application deployment for 5G vertical applications. You can see everything we do here linked directly to the challenge from the robot community or from the 5G and 6G beyond. We are trying to address the transparency, scalability, deployment problem faced by the distributed robotics. What we deliver exactly, so for this project, we are building up an ecosystem and a deployment environment. This environment will help robot developer to build large-scale distributed robotics. At the same time, this environment will help the network service provider to deliver the network services more efficiently. How can we do that? Effectively, we have 2 components in the core of the 5GR software or 5GR ecosystem. One of them is called reference network applications. This is showing you how to access the ambient intelligence or surrounding environment. My colleague will do the demonstration explaining how do they do the network application, follow my presentation later today. Another one is called middleware. This middleware reflecting the capability of the robot on accessing the ambient environment and how to access the intelligence of the surrounding environment on demand. This is about our 5G middleware. We will have demonstration and the presentation in the afternoon session to show how do we implement the middleware and the model of the middleware to help the on-demand access. So combine them together. We are claiming this is some sort of adaptive autonomy of the robot under the digital world for frictionless integration between the vertical and the network. So that is our ambition over here. And then my colleague will do the demonstration today, and tomorrow they will give you the testbed example, tutorials to show how can you build your own distributed applications with the modern capability of the digital world. A brief summary of our deployment model. For the ecosystem of 5G era, the deployment model is based on platform as a service. It separates the vertical application from the testbed. So our targeted user group, a two group of people, and first is administrators. This is about people from networking background. They provide the testbed. They are the administrators on the security policy, administrator of the platforms. And second group of user we are focusing on, this is about the vertical user. So they are the robot application developers. We are helping both of them to deliver the best service for as much as possible. The deployment procedure is divided into day 0, day 1, day 2. You can see that we have complete isolation between the administrators and vertical users. What I mean here is that for administrators, you have your networking knowledge, you have your security knowledge. You don't like to know the details about the robot planning, SLAM, fair enough. So you will be focused on the deployment of the middleware, onboarding of the resources. You don't need to worry about that. So that is focused on the day 0 and day 1 in the green part. And then for vertical user, on the robot developer, you have your algorithm. You know roles. You know what is the best way to build the behavior of your robot, but you really don't care, or you don't really, you're not used to worry about the topology, the slicing, the different kind of compute resource restrictions. Fair enough, you focus on your semantics, you focus on your robot information, you're offloading your task on demand, then you have your day 1 and day 2. We do the isolation for you so you can focus on your individual part, and then we will glue them together as the adaptive autonomy eventually to deliver our service. So that is kind of a philosophy we have in the project, and we will show you more examples in the coming sessions. Agenda today, and we will start with the 5G reference network application for robotics. We'll give you examples. How can you talk to the network applications? How to run and deploy the reference network application without the middleware? Where can you get more information about our software? And then in the afternoon session, we will show you how to do the middleware. And then with middleware, how can you do the onboarding, task offloading, edge switch over, and then what are the expectations of robot developer on distributed robotics. Tomorrow, we will give you more examples about the testbed, helping the 5G and helping the distributed robotics, use case scenario, and some hands-on experience with the testbed. And then we give some quick tutorial sessions about how to create your own network applications. How can you import the network application you created into the middleware? How can you integrate the semantic information into the 5G era? We want to collect the feedback and discuss with you. We don't want this to be a single demonstration. We want to hear from our developer or external developers on your opinion for our development. Based on your opinion, we will revise our project development, deliver more software for you. And we will have our hackathon followed by the webinar. Hopefully you can do it yourself for everything we demonstrated today. The presenter, many thanks for the contributors from the 5G era consulting. We have Michal from Brunner University of Technology to cover the network application, reference network applications. We have Bartosz and Adrian from University of Bedfordshire to work on the middleware deployment. We have William from Robotics Automation to share his experience on distributed robot development. And we have Anestis from IQU for sharing the knowledge about the test bed. So that's the presenter we have. 5G era is in the third year. We have lots of excited events scheduled ahead of us. As I just mentioned, next month, we will have a hackathon of 5G era to be delivered by the consulting. This is going to be a hybrid event. You are welcome to come to University of Bedfordshire. You can see the beautiful picture of our campus. And you can also join us online to do the hackathon together with our developer. In June, we will have our special session on distributed robotics with network applications in EU CNC Summit. And this is, I think from our discussion, this is going to be co-delivered with major company like Huawei together. And then we will have our ROS package released in the event. In September, we will have our transport, semi-autonomous transport robot use case to be delivered in Brno. In November, we will do the PPDR rescue robot in Athens. And next year in Cambridge, we will showcase our 5G solution for manufacturing as a service in Cambridge. So the many events piped up in the project to help people to use the development environment, to use the ecosystem of 5G era. I hope you can benefit from this movement in the future. That is pretty much my introduction for the whole event today, and my colleague will give you more details of the network applications, middleware, frameworks, and our way of solving the problem in the coming sessions. Any questions from you guys?
Thank you very much. Thank you very much, Rinch, for this amazing presentation. I don't see any questions in the chat. So if there are no questions from the audience live, then I think we can move. Thank you very much.
There was a question we have been asked in the previous sessions. It's mainly about the role solution we have is kind of a de facto standard in the world, and also they have been used by the industry. I think there is one version of roles for roles industry, helping the deployment of real-world applications in the factory. And then where is the position for 5G era? Because we're also talking about the distributed robotics application. I think the main answers to that question, if you come from robotic background, is here. It's about structured environment and unstructured environment. That is our main selling point in this project, because to my knowledge, most of the existing robot frameworks is designed for structured network environment. And we don't have a mature solution for unstructured real-world setting in terms of the network environment we listed over here. So contributing to the applications for the robot, distributed robot applications, so we feel quite confidently. This is our main feature to the robot community. And then our ROS release will also be focused on this area to have the more convenient development for the large scale distributed robotics. So that's just, the common question we got asked in the introduction to the project. And obviously the transparency and scalability is an issue which is focused on the 6G community, but there are lots of issues in the real world implementation. We are the actual use case in the real world, and then we will see how can we benefit from that moment. That's pretty much what I want to add, and this is a common question we are asking. Right, I guess this is my session. Let's move on. I will stop sharing here.
Okay, great. Thank you very much. Thank you very much, Alberto. So for our next presentation, which will be delivered by Michal Capinus, they will discuss the 5G era reference network applications for robotics, giving us the current examples. How do we talk to a network application? How do we run and deploy a reference network application without the need of middleware? And where can we get more information about these reference network applications for robotics? So Michal, the floor is yours. Thank you very much.
Hello everybody, my name is Michal Capinus and I work and study at the Brno University of Technology, and today I will talk about the unified communication interface which enables the robot to communicate with the remotely deployed applications over the publicly available networks. Besides, I will present some existing network applications which uses this communication interface. I will start my talk with a general description of robotic and network applications. Then we will take a look on how to talk with such a network application, or how the robot can talk with such a network application. We will then take a look on our proposed unified communication interface and how to use it to create a network application. Then we will take a look if it's necessary for the network application to be glued to one computer, or if we can spread it all over the globe and make it distributed across many machines. We will then see our reference network application, which was created using the proposed unified communication interface. And we will, of course, take a look on how to run such a network application. After that, we will see what tools are available for the robot to communicate with the network application. And in the end, I will show you some more examples of existing network application which uses the unified communication interface, and we will as well take a look on where to get more information about this communication interface and our reference network application. So first of all, what is the robotic application? Most of the robots need somehow process the data from their sensors, and they need to do a lot of various tasks. Some of the tasks employs, for example, computer vision applications, for example, object detections or tracking. So every mobile robot needs to see what's in front of him to be able to avoid it when he's moving. The robot which should communicate with the human needs to know where the human is, so it needs to detect the human, and many other examples of object detection usage in robotic applications. The robot also needs to know where he is. So for mobile robots, it's crucial to do the mapping of the environment and to localize himself in the environment. So the localization and navigation is another example of robotic application. And the robot usually also needs to store some data, because during the operation of the robot, many data is created from the sensor or from the logs of the robot, and so on. So a lot of robots needs to store this data either for later diagnostics, or maybe for training some neural networks for future operations and so on. All of these tasks, all of these robotic applications needs some computing power. And the more applications the robot uses, the more computing power it needs. But on the other hand, adding computing power increases the price of the robot, it increases its weight, and it increases its power consumption. Therefore, it would be nice to have a way of how to offload these tasks to some other computer, because it will decrease the cost of the robot and of course the other stuff I told. The other problem is that not all of the tasks on the robot needs to be run all the time. For example, with autonomous vehicle, when there is a need to cross some crossroads, or for the autonomous vehicle, when it approaches a train crossing, it needs to detect whether there is a train moving on the crossing, but it only needs to detect the train when it approaches the crossing and not all the time. But the hardware, which is used for detection of the train, needs to be present on the robot all the time, because the robot cannot get the hardware during its operation. So the hardware is presented, but it's not used most of the time when the robot operates. Therefore, we can use network applications to solve these problems, and we can offload the processing of the sensory data or any other kind of data to some dedicated computers, because these computers are usually located in some server rooms. When they have access to high-speed internet, they have access to proper power supply, and they can work much more efficiently than the computers on the robot. The network application run on the server can provide various functionality, such as storage functionality, processing of the data, and also a lot of other things for the robot. When using the cloud, the processing of some task could be spread to not one computer, but to many computers all over the world. The robot doesn't care where his data are processed. He only cares about the results and how fast he can obtain them. So with the cloud, we can efficiently use the available resources, because we can select the hardware which is in a perfect location for the robot based on the required latency, required throughput, or required processing power, and therefore it makes better utilization of the available resources. On the other hand, when it comes to stateful services, there could be a problem, because the stateful services requires some internal model which needs to be shared between the computers which process the data on the robot. So in case when we use the more than one computing machine to process the robotic data, this needs to be taken into account. So now, when we know what is robotic application and what is network application, we can see how the robot can talk actually with the network application. Because in our university we like robots, we use robots, and we made a lot of robotic applications in the past. The first thing that came to our mind when we were thinking about how to create a distributed application which could remotely talk with the robot, was the robotic operation system, because we had quite a lot of experience with it, and we knew that it can work across multiple machines, and it can seamlessly connect robots with other computers and provide the data channels for transferring data between these computers. So we started with it, but it showed up that the ROS is great in times when you have all computers in the network under one administration, because and in the one segment of the network, because for the ROS you need complete bidirectional connectivity between all pairs of machines on all ports. You need to synchronize time between all these machines for all functionality to work. And moreover, it expects reliable network connectivity, which does not have to be always the case when using the publicly available networks. Moreover, for all nodes to be, all node needs to know where the ROS core is running, the ROS master is running. So when it comes to multiple machines, you can make the ROS master publicly available and point all other machines to this one computer. So it's not a problem to discover the ROS master over the internet. But once the ROS master is discovered, all of the processing nodes still needs to see each other. And because in ROS, when one node wants to talk with another one, it needs to see the host of the other node, and it needs to also see all its ports, because the ports for communication are selected randomly. Therefore, it's impossible to use, for example, NET or port forwarding of selected port, because, as I said, all of the ports needs to be selected. So, as a summary, it is quite easy to discover the ROS master over the internet, but it's difficult or impossible to achieve the peer-to-peer communication. The only way is to create a virtual private network. But again, when it comes to the public internet and when it comes to public cloud providers, it could be a problem to set up the proper VPN with the security restrictions. So we decided not to use ROS for these network applications. The other possibility was using the ROS2, because it's newer, it claims that it has better network capabilities, so we decided to try it. And of course it uses the DDS, so it's a bit of magic of how it does the discovery of the nodes. In the ROS2 there is no master, so there is no way of how to point the individual node to one point where which provides the communication between or discovery between all of the nodes. So all of the nodes see each other using this magic DDS, but this DDS requires UDP multicast, which is again problem when it comes to the internet or the public networks, because the multicast does not work natively with the routers. So again, you need to use some virtual private network, but on the layer 2 to be able to use the UDP multicast. And again, some cloud providers such as AWS have problems with this, and it's difficult due to their security restrictions to create such a VPN and to successfully deploy ROS2 application cloud. To do it, you need relatively lot of low-level network configuration on the robot and the cloud, and that's again quite hard in multi-administration environment. The ROS2 can utilize the DDS router, which was designed to do exactly this, to route DDS traffic from one network to the other through the internet. But it's only available for one of the DDS providers in ROS2, and it requires ROS2 on both robot and cloud. So when it comes to supporting the ROS1 robots, which is still the thing nowadays, it requires quite a lot of added complexity, because you need to set up some ROS1 to ROS2 bridge. Then you need to set up the ROS2 communication between the robot and the cloud, and moreover, all of the network application needs to be using the ROS2, which is not always necessary for these applications. So as a summary, for this ROS2 thing, it's very hard to provide full discoverability of all nodes over the internet. But after that, because the ports numbers are selected deterministically with some of the DES providers, it could be run over the NATs and firewalls. But again, for the lot of complexity added, we decided not to use the ROS2 as well. So we came up with so-called unified communication interface. This unified communication interface uses two technologies. It uses the REST, or the HTTP endpoint, for the communication from the robot to the network application. So to successfully make a connection from the robot to the network application, you only need the address of the network application and the port where the network application's web server is listening. So this communication works from behind the net. It could be easily, the ports could be easily forwarded. So this works over the internet, and it uses the standard communication way. For obtaining some data from the network application to the robot, we are using the WebSockets. So once the connection to the network application is made from using the HTTP endpoint, the WebSocket is opened from the robot to the network application, and therefore we have bidirectional communication channel for sending data and obtaining results. The application interface is fairly easy, it's fairly simple. In the first step to start communication with network application is to call the register endpoint, which can include some configuration data for network application. This data are network application specific, so each network application could have different config data. For example, in case of object detection, you can say that I only care about detection of human, or only detection of cars. And for other application, you can use different configuration. The network application will then respond with acknowledge, and after that the robot initiate the socket.io connection, which will create WebSocket, and therefore we have bidirectional connection to the network application. After that, the robot can start sending some data with different data channels, which I will show you on the next slide, and it can receive the results using the WebSocket. Once the robot does not need the network application anymore, it can call the disconnect endpoint, and also it will disconnect the WebSockets. For the data channels, in our reference implementation, we support 3 different data channels. It could be the easiest one, the HTTP data channel, where the network application provides an endpoint for two provides two endpoints, one for sending images with timestamps and other optional data, and with the frame, of course, which is sent as a JPEG. And the other endpoint is JSON endpoint, which can be used to send any kind of JSON data. So anything which is JSON serializable could be sent over this endpoint. Besides this data channel, there is also the WebSocket channel, which is in the default case is only used for obtaining the results, but it also can be used for sending the data. So there are again two channels, one channel for the images and one channel for the JSON data. If the robot needs to send a lot of image data from the cameras, it can use the GStreamer for this, which can encode the images to the H.264 stream and send it to the network application. The life cycle of the network application is again quite simple. When it starts, it waits for connections from the robot. When the robot wants to register, it will create a session and the task handler for it. The task handler contains the data of the robot and the address of the robot, so it can be not address, ID of the robot, so it can be identified later with later connections. One of the parameters which can be sent in the register endpoint is if the robot wants to use the GStreamer. If so, it will create the GStreamer pipeline and add the port number to the response for the robot. And in both cases, it will respond to the robot with the acknowledge. After that, the robot can call the connect endpoint, which needs to be called after the robot is successfully registered. And if it is, it will create the WebSocket connection for the results and again responds with the acknowledge. After that, the robot can start sending data, obtaining the results, and thus do all the other stuff. And once everything is done, the robot can disconnect from the network application, which will cause the cleanup of all the resources available for the robot. And again, it will emit a response for the robot. As I said before in this presentation, there are two types of services which could be provided by the network application, and these services could either be stateful or stateless. The difference between these two services is that the stateful services needs to hold the data model, which is based on the previously received data. The model could be as simple as just a collection of the previously received images, or it can be some proper data model based on the received data. In the stateless variant, the application only responds to the currently received data, so it does not hold any old data or any model based on the old data. This implicates that the stateful service needs to synchronize all the computing nodes. Of course, in the case when there is more than one computing node, so in case of distributed manner, and the model needs to be shared between all the computing nodes, and therefore scaling of such a service is difficult. On the other hand, the stateless service does not need synchronization between the computing nodes because it does not have any model to be synchronized. It does not contain model, so it does not have to be shared, and it's fairly easy to scale such a service because you can just adding or removing the computing nodes at will, and they will start to taking the data from the robot and processing them. For this reason, we defined two types of network application, and the one is the standalone network application, the other is the distributed network application. The standalone network application means that the computing node is connected directly to the network application interface. So it's one application, one computer. Therefore, it can be easily deployed anywhere, and it can achieve low latency because the data are processed directly in the application. But on the other hand, it could be limited performance because there is only one worker, and it has lower scalability because you cannot scale it over more computers at will. On the other hand, because of lack of this distribution of the services, it is ideal for stateful services such as object tracking, because all the data are in one application. With the distributed network application, the network application is divided into two parts. The one part is the service or the network application interface, which communicates with robots and which receives the data from the robots. And the other part is the worker or computing node. And because this is divided, you can deploy a large number of these workers or computing nodes to different computers on different parts of the world, and they receives the data to be processed from the network application interface and returns the results to the network application interface, which then sends the data back to the robots. Because of that, it's much more easily scalable, but it's not ideal for the stateful services. It's ideal for the stateless services because you don't have to share the model, and so it's ideal for example, object detection. The downside of this approach is it usually involves a higher latency because the data are not coming directly to the computing node, but they come to the network application interface, and then they are redistributed to the computing nodes. The other downside of this approach is that you need to somehow solve this way of how to distribute the data from the interface to the workers. In our reference network application, we are using the Celery and the RabbitMQ and the Redis for distributing the tasks evenly across all the workers, and because of that, we can easily change the number of the workers on the fly. So that was it for the description of the interface and the description of the life cycle of the network application. Now we can take a look briefly on our reference network application, which uses this unified communication interface. For the reference network application, we have selected the stateless object detection task, and we employed the Jolo V5 multi-class detector, which is based on detection. So it's state-of-the-art object detector, which can detect human, cars, trucks, and a lot of other objects with specified classes. And besides this heavy detector, the network application, the reference network application, also contains a lightweight OpenCV phase detector based on hard cascades, which can be used for fast and pretty accurate detection of human faces. We provided two versions of this network application. The one works on regular PC. It uses only the CPU for the computation, and in the variant of the multi-class detector, it can works approximately 17 FPS using this quite old CPU. And we also provided GPU variant, which is based on CUDA 11.7, and it can achieve approximately 53 frames per second using quite old GeForce GTX 1050. And it only uses around 750 megabytes of GPU RAM, so this network application could be deployed multiple times on the same card, so you can achieve even higher frames per second using this relatively cheap graphic card. We also created and we provided Docker images for this network application, which are of course Kubernetes compatible, so you can use this network application without installing any dependencies. You can just download the Docker image and run it. And we have several of these images. For example, for the standalone variant of object detection, we have CPU and GPU images, and we also have images for the distributed variant. So you can also try this variant. So now we can take a look on how to develop and test such a network application, or maybe how we developed our reference network application. So as the main requirement for usage of our unified control interface, communication interface, is following the required endpoints. We based our network application on Python, and we use the Flask server for providing the necessary endpoints, and we are using the Socket.io library for communication over the WebSockets. The Socket.io library could be used not only from the Python, but it can be used from the other programming languages. So it is multi-platform, and the network application does not have to be written in Python. It could be written in C++ or C# or anything else, and but still using the unified control interface, communication interface. With this reference network application, it's easy to install it using the virtual environments. There are guides of how to install it available on our GitHub, and the requirements for the network applications are available on Python package index. The only thing that is not available yet is the special version of OpenCV, which is required when you want to use GStreamer, because the OpenCV needs to be compiled with the support for the GStreamer, but it's not mandatory, and you can use the network application completely without the GStreamer. So we can take a look on how can you run this network application locally. So as you can see, I'm here on my desktop computer, and you can see that I'm inside this reference NetApp repository, inside the ERA5G object detection standalone package, and I have this interface.py script here, which I can run with the detector detection parameter. And once I run it, okay, there is some error. Probably someone's trying to connect to it. Okay, now it runs, and I can run the client application, which connects to the network application, and you can see that I'm receiving the data from the network application, and I'm receiving the results on the robot or on the client. I will connect to the computer. Just give me a second. And you can see the results from the cannot see. Now we can see the results from the network application. I'm sending there these images, and the network application provides the detection of persons and cars, and it gives me the results. So this running this network application locally as a Python script is great for development and for rapid updates of the network application, but it requires the setup of the development environment. So you need to install all the requirements, you need to install Python and OpenCV and other things. So it's not really meant for production, it's only meant, as I said, for development or simple testing of the application. The other way of how to run our network application is to use Docker, because as I said, we published the network application as a Docker image on the Docker Hub, so it's publicly available, and you can run it simply with this command where you specify that you want to publish the 5896 port, which is the default port for the network application, and you just select the variant of the network application, and if I run it, it looks exactly the same as when I was running it locally, and I can run the client, and again it will connect to the network application, sends the data, and receives the results, which can be again seen here. So when running as a Docker, it's suitable for simple deployment. For example, when you don't want to use middleware for some reason, or cannot use middleware for some reason, you can run it as a simple Docker image on your selected server. It can also be used to run the locally built images during the development. And compared to the manual run, it simplifies the scalability of the service, as you can run multiple instances quite simply. Besides, apart from the Docker, you don't need to install any dependencies for this way of run, so you can download the available network application and just run it without installing the dependencies. And you can also use it for development, because Docker supports so-called dev containers, which enables you to connect with your programming IDE to the Docker container and use it for development. The other way of how to run the network application is to use Kubernetes. So in this terminal you can see that I have middleware deployed, but I will not use it for this demonstration. But I will use my deployment file, where I have defined one deployment, which is the same Docker image as used before. So NetApp Object Detection Standalone CPU on this 5896 port. And I also define a NetApp service as a load balancer, so the interface of the network application is available. So I can apply this deployment, and you can see that the pod with the network application is created, as well as the NetApp service with external IP. So I can set this address for the client application, and it will be able to connect to the network application and provide the same functionality as before. And we can use the kubectl delete to delete both the deployment and the service. So usage of Kubernetes for deployment of the network application is the best way for the production deployment, as it greatly improves the scalability of the network application and makes it fairly easy to scale these network applications over multiple computers. It also simplifies the deployment over clusters of multiple computers, but on the other hand, it needs more configuration than the simple Docker. Okay, so I have shown you how to run the network application, and you also saw a piece of the client application which was talking to the network application, and now we can take a deeper look on this client application. It is provided in the form of Python free library. At the moment we support the 3.8, 3.9 and 3.10 versions of the Python. This library could be easily integrated with robot specific code, so you can integrate this library inside your robot controller. It has support classes for GStream communication, so you can use it seamlessly. And we also provide you with the extended version of this client application, which allows to communicate also with the middleware. So you can use the client library to actually deploy the network application using the middleware, and after that you can start the communication with the network application immediately. The Python library is consisted of two main classes. The first one is NetApp client base, which provides the necessary methods for communication with the network application. It allows you to register with the application, and it only needs to know the location of the network application, so the host name and the port. And it needs or it allows you to pass some arguments to the network application. So it is the configuration for the network application I was describing before. This register method calls the register endpoint on the network application and also the connect endpoint on the network application. So this method will create also the result WebSocket channel. When the robot is connected to the network application, it can start using these methods for passing the data. So as I showed in the data channel slide, you can use HTTP or WebSockets for passing the data, and it could be either images or some JSON. And once the robot is done with the network application, it can disconnect from it, and it will close the connection to the network application. If you want to communicate with the middleware as well from using the client library, you can use the extended version of this class, which is called NetApp Client, which is inherited from the NetApp Client base. And it provides you with some methods for connecting to the middleware on the specified address and with the specified user and password. You can call run task to actually deploy a NetApp and connect to it. So you need the task ID and robot ID for it, which will be covered in the afternoon session. Once the NetApp is being deployed, you can use these methods for waiting until the NetApp is ready, and after that you can load the NetApp address and connect to it but you can either do it manually, or this could be handled automatically with the run task method. There are also some support classes which are using for example, sending data over the GStreamer. So this is thread-based class which connects to the GStreamer pipeline, and it can be used for sending the images over this GStreamer pipeline. There is also a middleware resource checker class which is used for communicating with the middleware, and it can read the status of the deployed network application. So you can see if the network application is ready or not, or you can wait until the resource is ready. So we can take a deeper look on the Python library. So I will again start some network application, and we can see this client application. So this is the application which runs on a robot and communicates with the network application. To start the communication, you only need to create a instance of NetApp client base class or object, and you will pass some callback function which is called when the results arrive from the network application. And after that, you can register with the network application on the selected address and selected port. Once this is done, you can start sending the data. So in this case, you can read either some data from camera or from file, and in the loop you can read the camera data or the file data. You can resize them, and after that you can pass them to the network application together with some timestamp. Once the piece of data is processed, it's the callback is called. So this getResult callback is called, and you can see the results. So these are the JSONs which were printed when I was running this client application, and you can somehow process the data. So for example, use them to draw these bounding boxes around the detected objects. So if I run it again, you can see it works just like before. And because the network application can handle multiple clients at once, I can run another client application. So here you can see it reads the data from the web camera, while the other client reads the data from the file, and both of them are processed simultaneously on the NetApp, and the results are propagated back to the client application. In this case, this network application runs on my desktop computer, and this client application runs on the same computer, but this other client application runs on my laptop, and the network the network application runs on the computer which is behind NAT, and the port is forwarded on the router, so you can communicate with it from the outside. So since the client library is written in Python, it could be simply integrated into the robot which uses ROS. And to see how it's done, you can see. I will leave the NetApp running, and I will switch here where I have my ROS1 node, which works exactly the same as the previous example, I will initialize the ROS node, NetApp client, and I will again create an instance of NetApp client base class with the results callback, and I will register with the network application, and after that I create the subscriber for some input image topic, and I will create a publisher for the results, and in the image callback I will just transfer the ROS image inside the OpenCV image, and I can send it to the network application using some of the specified methods, for example the HTTP method, just like before. In the results callback I can again read the results and print the bounding boxes inside the image, and publish the image over the results publisher. So if I run it, I need to start the ROS core. I need some image data. So for example, this USB cam node, and we can see the images from the camera here. So I've pointed the web camera outside of my window, so there are some cars. And now we can do ROS topic HZ results. So we'll see if there are some results. There are no results yet, but if we'll run the NetApp reference client node with the input image redirected to the USB cam image row, you can see that the results are published almost immediately, and we can use the image view to see the results. So you can see the network application is detecting the cars. These are not detected probably because they are behind the trees. I can move with the camera, and yeah, and you can see it start to detect it. Also this truck, this one. So this is how you can use the Python client library from the ROS1. But the problem is that you can only use this Python library in ROS Noetic because the ROS Noetic is the only distribution of ROS1 which uses the Python 3, which is also used by the client library and the network application. But all the ROS distributions prior to the Noetic uses the Python 2, which is incompatible with the network application. Therefore, we have created a Docker image which has a service topic interface for working with all the ROS, and this Docker image provides you with the ROS service to create a connection to the network application, and you can pass the image data using the ROS topic to the client, and it will translate them to the HTTP REST or WebSocket communication data channel and pass them to the network application, receives the results over the WebSocket, and pass the results to the ROS topic. So we can take a look on that. Again, I will try to read the results. There are no results yet. So I will start this Docker image, which is Bat5G era Noetic client. And as you can see, no messages yet, but ROS service lists the NetApp Connect service. ROS service call NetApp Connect, and it requires the address of the network application, it requires the port number, the input topic with image data, and the output topic it should provide you with. So if I call it like this, because the network application runs here on my computer on this port, and I have this input topic data, you see I can receive again almost immediately the results from the network application, and I can again see the result here. Because of this approach, we can support also older versions of ROS. So we have tested it with Melodic and with Indigo ROS, so quite old versions of ROS. And if I'm not mistaken, Adrian in the afternoon session will show you the example run of this service with some robots. So that was it for the reference network application and the client library. And now I will show you some examples of two network applications which are based on our communication interface. The first one is the train detector network application, which would be used by the Bring Auto. And the reason why this network application is requested is that when the autonomous vehicle moves around on some roads in some area, it can cross the train crossing, and it makes sure that it wants to make sure that it will not collide with the train, because that would not be very nice. So this network application is meant to run in the way that the robot will approach the train crossing. It will look if there are any trains moving, and if there are no trains, it can safely cross the train crossing. The first version of this application was based on this Jetson Xavier platform, which was mounted directly on the robot, and it uses two cameras to look on both sides of the train crossing. And it uses some custom-made Flask server, which was receiving the video frames from the cameras. It uses the Jolovi 5 Tensor RT version of the object detectors to detect the train, and it uses some sort tracker to find key points on the train detected, and it uses KLT to track these points. As you can see, there is another moving object, but because it's not a train, it's not taken into account from this application. And for the reasons I was talking about in the beginning of my presentation, we wanted to make this application not on the dedicated hardware on the robot, but we want to make it into cloud or maybe edge device to relieve the robots from the hardware requirements. And therefore we have created, or not we, but our partners created the network application which is suitable for the cloud, and it uses the proposed network application interface, and it again receives the data just like before. It uses the more heavy object detector based on MMCV, which can run on dedicated graphic cards, so it's much faster than this this Tensor RT detector on the NVIDIA Jetson. Currently it uses the same tracker and key point tracker as the original version, but because of usage of this dedicated hardware, we can implement more sophisticated methods of key point extraction and tracking, such as deep sort and superglue. and we can fully use this heavy graphic card. The other network application which is created using our communication interface is the collision avoidance network application, which could be used for autonomous vehicles to early detection of possible collisions with other moving objects. This network application uses the calibrated camera on the robot or on the autonomous vehicle to detect the objects around, and it anticipates the path of, or it predicts the path of the objects to warn the operator or the autonomous vehicle. It works like this. There is the autonomous vehicle with the camera installed, and there is some specified caution zone where no moving objects are allowed, and it's in the direction of the vehicle movement. And there is a tracked object which is being and its predicted path is being calculated. So even if it's not inside the caution zone, it's tracked, and we can warn the robot of the approaching objects. This network application uses again the Jolo V5, and it uses the sort tracker to track the objects, and as it projects the objects to the vehicle space, it needs to the camera needs to be calibrated and rectified, This network applications generates some signals such as caution, which means the caution means that the moving object is about to enter the caution zone, but it's not dangerous yet. The warning signal means that the object is located inside the caution zone. And the danger signal is generated once the object will likely collide with the vehicle. So it does not have to be inside the caution zone necessarily, but its path will still be predicted, and the signal will be generated once it looks like it will collide with the robot. This is the diagram of this application. It's consisted of several packages. The core service uses the Jolo detector. It extracts the geometry from the scene, uses the detection and the sort algorithm to detect and track moving objects, and it predicts the collisions. The service part of this network application uses the packages from our RFIG interface package and reference network application package for the object detections and also for the communication with the client. And the client uses the client is based on ROS2 and uses the client Python library to communicate with the network application. And to actually see the how this network application works, you can see this video where the robot is moving on the road, and there is a car approaching from the right. At the moment it's being detected. You can see it here. Now the caution signal is generated because the car entered the caution zone, and because it brakes heavily, that it's predicted that the path of the car will collide with the robot, so it creates the warning and the danger signal. And now the car is away from the robot, so no signals are emitted anymore. In this other case, you can again see the camera from the robot, and again there is a car which will likely collide with the robot, and therefore the danger signal is emitted, although the warning signal is not emitted because the car is not in the caution zone. Okay, so that was it for the presentation, and in the last part I will show you where you can get more information of the network application, the reference network application, and other packages we provide you with. The first repository is the ERA5G client repository, which contains all the Python libraries for the client application. It also contains some general examples of how to use the client library, and therefore it is interesting for the robot developers which needs to integrate the network application into their robots. The other repository is the ERA5G interface repository, which uses the Python classes for network applications. Therefore it is interesting for the developers of the network applications. Last but not least repository is the reference network application repository, which contains, of course, the reference network application, some more specific examples of how to use this network application and how to connect to it. Therefore, it is interesting for everyone, I hope. So please use our software, send us your ideas, send us the problems you are facing, send us the task you want to make as network applications, or any questions using or any questions regarding the network applications or the client. You can either use emails or preferably the GitHub issue system, and also feel free to create any pull requests with additional functionality or enhancement of the existing software or anything else. And thank you for listening, and if you have any questions, feel free to ask me.
Great. Thank you very much, Michal. Thank you very much for this excellent and really interesting presentation. So we do have some questions in the chat, if it's okay to give you some. So for the first one is, compared to the ROS native communication, how efficient is the newly defined 5G ERA reference communication interface, in your opinion?
Yes, comparing with the ROS communication, the efficiency is similar, but you can easily achieve the communication over the internet. So that's the main reason why to use this kind of interaction.
Great, thank you very much. Thank you, Michal. Another question is, so ROS communication, like SLAM, requires multiple topics to be considered at the same time. So the question is, how can we convert the kind of ROS communication into the REST communication that is used by the 5G ERA reference network applications?
Yes. Well, for the camera images, for the data from the camera, there are methods for sending this data available on the client, which will automatically compress the data into JPEG format and send it to the network application. And you can also add some metadata for these channels, so you can simulate sending images from different sources. So if you have like 3 topics with cameras, you can use 3 of these methods with different metadata, which will define or identifies each of the camera, and use this to send the data. For the other kinds of data, for example, the point clouds, you can serialize them into the JSON and send them over the JSON endpoint.
Okay, great. Thank you very much. Then another question is that, so the network applications as being referred by the telco, the communication community, are usually designed and optimized for managing network resources. So we understand from the presentations before that that our project, the 5G era reference network application, is a bit different than that design-wise. So, what could you give us a few words about the design principles behind the reference network applications in our project?
Yes, for the reference network application, or generally network applications in the scope of 5G era project, we expect that the platform is provided by the middleware. So we only care about the pure communication with the network application, and we can leave the rest to the middleware, which will create the platform for us.
Okay, great. Thank you very much. Then two more questions. One of them is how do you manage the network resources and slicing within the reference network applications?
Yes, I think the answer will be similar to the previous one. We plan to use the middleware to handle this, or the slice manager, which is being developed in this project. And so from the point of the robot or of the network application, we expect that this is somehow magically solved by these services for us.
Thank you very much. And lastly, how do we scale the stateful services for robots?
How do we scale the stateful services?
Yes.
Yeah, that's difficult. We can, of course, deploy more of the network applications. So one robot can communicate with two network applications at the time. You can deploy more of them, but in case you want to use or increase the performance of one stateful service, you need, of course, somehow synchronize the results from all of the model from all of the workers, for example, through the Redis database, or somehow else. You just need to distribute the model between all the workers and synchronize them.
May I add some additional comment for this one?
Of course, please.
Yeah, this is a very interesting issue, scaling of the stateful services, and we have a persistent backend from Redis, is mentioned by Michal, and so the information can be stored in the persistent storage in the Redis. So you can, if we have a map generated by the robot operation, so those maps will be stored in a persistent way. The more interesting question is mentioned by Michal is synchronization. And for the stateful service, especially stateful services accessed by multiple robots at the same time, maintain a strong synchronization is kind of impossible. So we could do something called a weak synchronization using CQRS, command query segregation. So effectively, this is some sort of event sourcing pattern. Let's say in the map, we can have different versions of map persisted in the backend at the same time. And then for the updating of the map, they will be injected to the backend when the robot have new information. So this is for the writing of the information into the backend. And then for reading the information from the backend, so because this is weak persistence, we don't need the latest information. We will have a reading model to provide the ready-made map to the robot who is asking for this information. So this is kind of a patterns. I think it's used by microservices. We are trying to extend them into robotics. Hence, for robot application, especially like a coordination of multi-robot on SLAM, can take advantage of the stateful service to be scaled up in the application. Yeah, that's the additional answer we've adding here. So in the new future release of our software, you will see this kind of implementation for the 5G applications. That's it.
Very great. Thank you, Rishi. Thank you for this extra information and your comments. Thank you very much. Great. I will just give an opportunity to anyone who wants to unmute their mic if there are any further questions not given in the chat. Now, I'll take that as a no. So thank you very much again, Michal, for the presentation. So this is the first section of our webinar done. We will see you back here at 3 o'clock CT or 4 o'clock Greece and Cyprus time and 2 o'clock UK time for the next session. Thank you very much, everyone. Have a nice afternoon and see you soon.
Thank you very much, and thank you for the presentation from Michal, and then looking forward to see you in the afternoon and tomorrow.
Yeah, great. Looking forward. Thank you.
Bye-bye.
Bye-bye.
Thank you.
Stop
Bye.
recording. No?
Yes.
So hello everyone and welcome to this afternoon session of today's webinar in which we'll cover the middleware for deploying the network applications. My name is Bartosz Bratus and I'm from the University of Bedfordshire, and in this session me and my colleague Adrian will show you the process of how to integrate the 5G middleware into the robotic applications. As Andreas has mentioned briefly before, our today's agenda will cover what exactly is the 5G era middleware. You have heard it previously in the morning session from Michal. In this session, we'll expand more on what exactly is the 5G era middleware and what purpose it serves. Later on, we'll continue with the middleware onboarding and the requirements that it has to use it with the example network applications like object detection. Afterwards, I'll pass my microphone to Adrian, and he will explain to us the process of onboarding the robot, deploying and using network application from the onboarded robot. And then we'll go back to me, where I will cover the switchover functionality of the middleware. And then I'll also move on and give my microphone to Guillaume to present us the robot developer point of view in integrating the 5G middleware into their production environment. Afterwards, we'll finish with a little Q&A session. So starting, what is exactly the 5G middleware? And the 5G middleware for us is a transparent distributed system that serves as an intermediary between the robot and the network applications. Thanks to this 5G middleware, we are able to support a variety of the network applications and manage them and orchestrate their deployment, their usage, and the removal of those network applications in the on-demand manner. The network applications in the 5G middleware are deployed only when there is a need to utilize such a network applications to save the resources used to provide the better scalability of the system. In the 5G middleware, we are using the semantic knowledge to create the deployment configurations and to utilize the network applications themselves. To get to know more about the details of the 5G middleware, you can track our progress on the GitHub with the link that is visible on this slide. But actually, why do we create this 5G middleware in the first place? There are a few reasons we are doing this. First one is the diversity of the network applications, how different they are. And the same comes with the resources. The resources that we are working on are heterogeneous. They're each they are different. We have to support multiple locations of the deployment. We have to support the orchestration process of those network applications. And finally, we have to glue this together to enable the virtual platform for this application. So when it comes to the network applications diversity, each network application can serve different purposes. As Michal showcased us on the morning session, the network applications could serve the purposes of the image or train detectors. This could be also SLAM or teleoperation applications. The network applications can be anything, and we have to support all of them. On top of this comes the different communication methods for the applications. Usually, right now, the vertical applications are using rows to communicate between each other. We have to support a newer standard of passing the messages and the data between the network application and the robot. So for this, except of the ROS communication standards, we also have to support protocols like REST or GStreamer and WebSockets. In addition, each network application has different runtime requirements, the resources that are needed for the correct functionality of the network application. For example, like Michal has mentioned in the morning session, some distributed variant of the network application may require us to additionally deploy RabbitMQ message broker or Redis cache to correctly process the data. The next challenge is how to combine the heterogeneous resources under one single umbrella. Each environment the network application will be running on has a different set of has a different specification. It could be the cloud machines that are managed by the third-party company. It could be in the local edge devices that process some low-intensive workloads locally, or also it could be the private data center of some specific company. And all of this has to be utilized under the 5G middleware. The next problem that we'll be facing is the resource orchestration. For the best operation and the quality of experience, the on-demand deployment is a must. With this comes the way how we will provision the resources and how we will manage their life cycle, for example, scaling, removing, and then also updating these resources. The additional challenge that we'll also have to cover is how to provide the static resources like maps for the SLAM network applications. And all of these problems have to be combined under one single umbrella for the virtual platform management. So as Renzi said in the introduction section, we want to shift the network-oriented infrastructure to give the more input to the vertical users, which are, in this case, the developers of the network applications. We want to enable them to be able to manage the infrastructure to utilize the applications that are required by them, and to connect the network scalability with the domain knowledge that they have. So what is exactly our solution? Our solution is a platform as a service that abstracts the infrastructure from the vertical users to allow them to provide the platform to run the services that are deployed on demand with all the complexity shifted away from them. This allows us to create the intermediary between the vertical application and the vertical applications that could be robot but not only the robot, and the remote network applications that will be providing the compute-intensive operations to these vertical applications. The 5G URA middleware is a distributed system which allows us to increase the availability and resiliency of the system by incorporating multiple locations of the middleware running in the same time to achieve so the middleware can be accessed at any time with with lower latency, which results in the increased quality of the service. Also, thanks to the distributed middleware being distributed system, it gives us the flexibility of the resources that we have under our hand. For example, one location that the middleware is running on can have a very good GPU support. So the network applications that are GPU intensive could run in there to provide the best quality of the service and the quality of experience. The system architecture of the middleware consists of multiple independent middleware instances running at the same time. Each middleware instance runs the self-contained Kubernetes cluster to allow for the better operability of the resources and easier management when it comes to managing the resources inside of this Kubernetes cluster. Though each middleware instances is cooperating with each other by using the backend synchronization service like Redis or message queues that are used for scheduling the deployment. And thanks to the multi-location orchestration, we are able to to provide the resources for the robot from multiple locations at once. So in this part, I will demonstrate what exactly is needed to deploy the middleware, how can we orchestrate the example network applications using semantic planning, and how to use the example network application with the USB camera. When it comes to deploying the middleware environment, all we need is just a locale or machine or virtual machine that is located in the cloud, which is accessible within the public or private network. The exact virtual machine configuration is available under the link in this presentation that you can follow later on. But to summarize it shortly, there are very small requirements that we need. First of all, we need a Kubernetes instance running on this virtual machine. And on top of this, there are a few small Kubernetes configuration manifests that allow us to configure the cluster in such a way that it is very easily usable. On top of this, we'll need a message queue, preferably RabbitMQ, to be able to integrate the multiple middleware instances running with each other, and Redis as our data storage for the persisting the data for the network applications. When it comes to the hardware requirements, we are dependent on the network applications themselves. The middleware itself is fairly lightweight and doesn't need a lot of the resources. The actual resource requirements are based on the type of the network applications that will be running and their amount. So the deployed middleware consists of the 5 services. The first one is the orchestrator, which is responsible for managing the resources in the Kubernetes cluster. The second one is Redis interface that provides us with the backend synchronization with the Redis database. Afterwards, we have one of the most important components of the system, which are the task planner and the resource planner. The task planner and the resource planner are cooperating together to translate the semantic knowledge given by the vertical users into the ready-to-use plan for the robot. And then they pass it later on to the orchestrator to deploy the specific plan for us. The last, we have a gateway, which is the entry point for the whole system. So how do we actually deploy the network application? How do we orchestrate it? As you have seen previously, in the morning session, Michal has mentioned that the middleware requires us to give the identifier of the task and the identifier of the robot. What it does behind the scenes is actually makes the NetApp client actually makes the REST call to the middleware to provide us with the plan for the specific robot and specific task, and then to deploy the resources to be able to use them. In this process, the task planner receives the call. It cooperates with the resource planner to select the most appropriate resources and to create the plan that will be returned as a response to our call. After the plan is created, it is passed to the orchestrator which deploys for us the NetApp object detection in this case. As you can see in this terminal output, we have a new application running, which is the NetApp object detection, and it is also correctly exposed so it can be accessed from the outside of this machine. So as the next step, I'll showcase how we can actually utilize the network application that we are deploying. The video demonstration that I'll be showing here is very similar to what Michal has been showcasing us with in the morning session. In this scenario, we are using the computer that is running ROS1, and we'll be requesting the deployment of the new network application and connecting the USB camera output from the local computer to perform the image detection on this computer. As you can see, right now we are configuring the ROS master, and we are listing the topics to ensure that the USB camera is visible. Next, we are deploying the NetApp client that schedules the deployment of the NetApp object detection container. Alongside, now we can see that the NetApp object detection has been given its own unique IP address. So now we will start the Docker container to connect to this network application and to perform the image detection from the camera, which will be published on the results topic. And now, as you can see, we can see the output from the camera that has been processed by the object detection network application. And as you can see in the small image, we can see that the network application is correctly detecting the keyboard that we are looking on through this USB camera. And now it is also correctly detecting the water bottle that we have in front of us. In the end, when we'll finish our own task, the NetApp client will ask for the deletion of the unused resources, and they will be deleted from the Kubernetes cluster to free up the resources to make a place for the new network applications. But what we have presented in here is not the only thing that the middleware does. As middleware has some additional features that allow us to be platform independent. The middleware does not only run in the, for example, local edge or AWS cloud. We are aiming to be able to run the middleware in any location that has Kubernetes on. With the backend synchronization, we are able to synchronize the data between the running network applications to be later on reused by the robots. So let's say, for example, that one robot has been doing the slam in a specific area, and this robot has finished. But later on, the next robot would like to continue the work in the same location. We will be able to provide the same map for this robot to continue on the work that has been done already. Also, thanks to the middleware being a distributed system, we can achieve the high availability that later on is also supported by the edge switchover functionality, which we'll explain later on. As a distributed persistent storage that is running and that is utilized behind the scenes, we're able to provide the same data as a part of the backend synchronization to the stateful network applications. On top of this, we're also managing the security for the system to allow the access only to the specific robots that were onboarded in the middleware. But for this, I'll give my microphone to Adrian. Thank you for listening in this part. And do you have any questions for now? If not,
we have some questions in the chat,
okay.
But if it's okay.
Okay,
I just left some time for the people in the if they want to raise their hand. Okay, so 5 questions for you so far. So first one, what are the hardware requirements of the 5G era middleware?
For the base hardware requirements, I would say that to be able to run a few network applications, I would say that the 4-core CPU with 16 gigs of RAM and preferably 100 gigabytes of storage or more would be enough for the example workload. But you have to have in mind that it will always depend on the type of the network applications that you will be running and how many of them you will be running. You will have to be able to scale the hardware alongside to your needs.
So yeah, so I guess we could potentially investigate at some point the scalability of such hardware. I would imagine that it would be a nice study for someone to have, let's say, or experimenters. Okay, great. Thank you very much. So second question is that, so we discussed that semantics is incorporated in the 5G era middleware. So what kind of intelligent behaviors do you expect to be enabled by this feature?
What kind of intelligent behavior do we expect is the intelligent selection of the network applications that are required to be able to provide the specific resources for the robot to perform the certain task. In this case, what we mean, let's assume that the robot wants to go from point A to point B. And this task for us is defined as a set of steps. This is the navigation and then the control of the robot, for example, and maybe an object detection to detect obstacles. So for this, the intelligence will have to know that it has to conduct 3 actions to perform a certain task, which needs the object detection service, it needs a navigation service, and possibly teleoperation if it cannot conduct the tasks by itself. This task we are assuming will be constructed from this semantic knowledge that is incorporated into the middleware that Adrian will showcase us in the later of this presentation.
Great, thank you very much. Thank you very much. So something more practical now as a question that was posed. What is the release schedule of the 5G era software?
We are aiming for a monthly releases with each having some new features or improving the existing features. Usually we are aiming to have 1 release each month.
Perfect. So looking forward to, so we'll keep the community updated for that.
The latest version that we have is 0.3, and I believe that by the hackathon you will be able to expect the release 0.4.
Great, that's good news. Perfect, thank you, Bartosz. So if one was to search, where can we find more examples of the 5G era deployment?
The more 5G era deployment examples will be showcased tomorrow. After the first presentation, we will showcase how we can incorporate our own network applications into the 5G middleware to be included in the planning process.
Okay. And we will make sure to upload this also as a side note to our channels, and then so it can be accessible. And then the last question, what is the difference between the deployment using the 5G middleware and the deployment using standard Kubernetes as shown in our session in the morning of the network applications?
The deployment, the difference between the standard deployment in the Kubernetes and the deployment in using 5G middleware is the fact that when using 5G middleware, we are able to construct much more sophisticated deployments that can be automatically parameterized to serve some additional middleware functions like monitoring of the resources, moving the resources between the required locations in the automated manner instead of doing this by ourselves.
Great, thank you. Those were the questions.
Okay.
So thank you very much for your presentation.
Thank you. I'll give my voice back to Adrian.
Yeah,
thank you very much.
Thank you very much. Okay, so moving on with our next presentation. So we will discuss the onboarding of robots to the 5G middleware, which will be presented by Adrian Ledinas. We will present the main challenges and the 5G era solution. We will follow by demonstration of the onboarding of the robots, plus a short Q&A as now. So Adrian, please, the floor is yours. Thank you very much.
Okay, good afternoon, everyone, and thanks for joining our afternoon session in the 5G era webinar. I will now begin my presentation, so I will kindly ask if you can see my screen.
Yes.
Okay, so again, my name is Adrian. I'm a PhD student at the University of Bedfordshire, and today I will be showcasing and explaining how to do the onboarding of any kind of robots into the 5G era middleware. And we will be taking some examples. We will be answering why we need to onboard our robots, why is this important, and yeah, we will have some demonstrations. So what is the main challenge over here? The main challenge is that we want to perform seamless integration of robotic systems with the 5G era middleware. So we have our robot in the lab, and we want our robot to be able to consume 5G era middleware. And to do that, we don't know what to do, and the solution is we will actually onboard the robot into the system, and then it will be automatically be able to request any kind of network application, any kind of resources, and it will benefit from all the middleware features like edge switchover, semantic construction of task sequence, validation of the robot being able to complete the task, and so on. Actually, very importantly, by onboarding the robot into the middleware, we bypass all the technical knowledge about network applications and testbed for the robot developer. So we are isolating our robot developer into the vertical application knowledge, and it doesn't have to take into consideration all the network topology, the testbed, and so on. So this is our challenge. What do we do to onboard our robot? So to onboard our robot, we have prepared a lot of resources, mainly a lot of documentation and some utilities to capture the information. So starting off, there is official 5G era onboarding documentation that you can follow. There is also some scripts to capture ROS-related data from the robot, since onboarding process actually involves sending a lot of information about the robot with regards to the ROS to the Redis backend, which is our database. We have also procured to all of you a couple of examples of already onboarded robots for you to play around. Okay, so what kind of information we are required for the onboarding of a robot? Mainly, we are concerned with ROS distribution and information about ROS nodes and topics. Also, available sensors and actuators. So the robot has a LiDAR, camera, and so on. That's very important for us to know, as the semantic planner in the middleware will be able to plan according to the robot specifications. We are also very interested in the type of locomotion system of the robot. So if the robot is actually a mobile robot and can do navigation, that's important, and also some miscellaneous like manufacturer, weight, ROS repository, and so on. And finally, I want to stress out that even we are considering a lot of ROS information here, we can also do onboarding of non-ROS robots into the system. So how do I do my onboarding? First of all, if you have a ROS robot, we will kindly ask you to download our utility to capture the ROS data. We will be showcasing a demonstration, but what is going to happen is there is some Python script that we have created that will query the ROS to capture information about the topics and the number of nodes and so on. And then we will complete this template that has been 50% completed by the Python script, and we will add the name of the robot and the company and so on. And then there is actually two possibilities for doing the actual onboarding, which includes using the Fightjera dashboard and using other programs like Postman or Insomnia to do the actual HTTP request. For the actual demonstration we will be showcasing today, we will be using Postman for doing onboarding of ISOI robot. Finally, we can validate that the onboarding was successful by looking into the dashboard or the Redis Insight, which is a visualization tool for the Redis database. And now our robot is able to speak with the middleware and to use it. So we will be doing demonstration. In this example, we will be onboarding ISOI Geek. So ISOI Geek is a social robot developed by a Spanish company, ISOI Robotics. ISOI is a social robot with ROS distribution Indigo, ROS1, and it has a camera, touch sensor, some head and face actuators. We can actually we have available the onboarding template for this robot. So we will actually be looking into it very quickly for you to have a look into how onboarding template actually looks. So actually, I'm gonna stop sharing 1 second. You may see we have our robot here. It is welcoming us Fightjera. And there is actually some welcome message we can play before running demonstration.
Welcome all to Fightjera. Thanks for joining. Hope you have a nice time.
Yeah, so robot will welcome us. So now what we are going to do is we will showcase a onboarding template. Okay, so this is our 5G era repository. Under utilities, there is onboarding template. And this is this is onboarding script, and this is the Python utility we have created to capture the ROS data. So basically, we will launch this script, and we will capture the robot. Basically, what's going on is we are querying Linux for ROS distribution, number of ROS nodes, and then we will do ROS node info for each of the nodes. And we will capture this into a dictionary, and we will get some output back. I will play a video of this very quickly. Yes. So here we are SSH into ISO robot. We can do ROS topic list. You will see that the robot has a lot of topics. It also has a lot of nodes. So we want to capture this information. So what we will launch this Python script, and it will basically start querying ROS all over the place, capturing many information. It will take a couple of seconds for this robot. Other robot with 1,000 or hundreds of nodes will take a couple of minutes. I will advance since it is actually taking a lot of time printing information, but it's finished. And then there is output, which is robot onboarding.json. By looking into it, we will see that program has actually included the relevant ROS information as a JSON file. Okay, so this is a video demonstration for capturing ROS data. Coming back, we have some examples available. As we were saying before, we have ISO and we have Kabuki base. So we'll look into, what is it? ISO. Yes. So very quickly, this is onboarding file of ISO. We will actually be using Postman to create this robot in the middleware. So what is going to happen is we just have to copy paste the template into the JSON, into the body of the request, and then we will click send. Before that, we need to log in and be registered, but that's outside of the scope. So very quickly, the information captured by the script is the ROS nodes field, and then there is other miscellaneous like robot weight, ROS repo, distribution, name, and so on. So for our robots using 5G middleware, we are hoping to create this kind of templates. We also have actuators, another kind of sensors, and yes. So let's do actual demonstration of onboarding. To do the onboarding, we need to be registered. So I will just log in. We are calling login endpoint, and I will get my token. Copy the token. And here in authorization, I will paste the token. Here is the template, and we will send it. We got response 200, which is okay. And now we have onboarded our robot with this ID. So if we go to Redis, we can actually try to look for the robot. We will query for robots. And our robot was 08 bed something. And here is the robot onboarded with information about ROS and so on. And this is pretty much the procedure for onboarding a robot. This is exactly what I have been explaining. We need to do registration and login before being able to onboard the robot. And we will get a new entry in the database. So with this, we are able to do the following thing. Basically, the middleware can validate and plan any robot request. So one of the questions we were having before is, what is the difference between using middleware and not using middleware? Well, one of the differences is that imagine robot requests two types of tasks. One, it wants to do navigation, and other task, it wants to do object detection. Well, this is a robot that cannot move. This is a static robot, even though it has legs. So when the robot asks for a navigation service, the middleware will say, okay, I know this robot. This robot doesn't have a locomotion system, so I will not deploy any network application for navigation, because obviously the robot will not be able to complete the task. Meaning that in this way, we are taking the appropriate measures to save our resources and to optimize them. As another example, if the robot requests object detection, the middleware will say, okay, robot actually has a camera in the right eye. I can see there is a ROS topic over there. So I will actually deploy this network application for the robot. And this is the kind of validation and planning we are able to do when the robot is it is onboarded. So we take all the semantic information, all the ROS information, and we can do very fancy planning. So this concludes onboarding session. And now we will be talking offloading a robot task on demand, which is the second step. We have our robot onboarded, and we now want to use the middleware to get some network applications deployed to have our robot complete some tasks. So what is the main challenge? Well, the main challenge is we want to perform seamless planning and deployment of necessary network applications for our robot to complete a task. And we want seamless connectivity of the deployed service with the robot. And obviously, we want some continuous update of the deployed resources for the robot to know, okay, my network application is still alive, I can still use it, and so on. So to do this, we have provided two kinds of interfaces for connecting the robot with the middleware. Our solution includes Action Client, Action Server, ROS versions for ROS 1 and ROS 2. They are also containerized in Docker. So you can either run it on the using Docker, or you can run it using normal ROS run, ROS launch. Our Action Client, Action Server is a very good solution when we have complex action sequence. So this means there are many network applications to be deployed in a sequence. First, I do a navigation, and then I don't want navigation, and I stop it, and I want teleoperation, and so on and so forth. So for complex task, where it involves a very long action sequence, in which we are very much interested in continuous tracking of the deployed network applications, we will use Action Client, Action Server. And then for fast testing, single action and service request, we have Python standalone script, which will also communicate with the middleware and deploy the necessary network applications. As I said, both solutions can be used. For simplicity's sake, in this demonstration, we will be using the Python. Anyhow, I will also explain very quickly how does both interfaces look. First one is the Action Client, Action Server, which uses those action goals for communication. And this action goal actually has a couple of properties, mainly involving the task ID and the action reference. So task ID means which action which high-level task I want to do. And then the action reference means which action from the action sequence I am currently in. So the action message is actually looking like this. It has task ID, task reference, and then in the feedback, there is information about the action sequence. So the robot knows what are the steps that I need to take to finally complete my high-level task. And we also have some feedback information about the resources. So I have deployed object detection. I want to make sure my object detection is still alive. I want to know what is the IP address of this network application. I will get all of this in the feedback section, and then there is also a string with results. So Action Client, Action Server works pretty much in a loop. So first of all, what is going to happen is that the robot will say, okay, I want to get a task completed. So I will send the ID of the task, and I will say that I am starting from action 0, meaning this is my very first attempt at trying to do this task. So the middleware, what is going to happen is it will receive the action, and it will try to log in into the into the the action server. Sorry, the action server will try to log into the Figera middleware. It will try to retrieve a plan according to the robot specifications. If the robot cannot achieve this task because it doesn't have a locomotion system or so on, it will be rejected, meaning that the action in terms of ROS will be changed to a status failed. If the plan is actually possible, then action server will return to action client saying, yes, this action goal has been accepted. You may now continue. So now the action client says, okay, I have received my action sequence, so I know the actions that I need to take step by step to complete my task. So action client will say, okay, I want the first action from my action sequence to be deployed. So it will send it to the action server. Action server will deploy with the help of middleware this network application, and it will come back to the robot, which is the action client, and says, okay, here is your resource deployed. Here is the IP address, and here is the status for you to know, and do whatever you want with it. So this would keep iteratively happening. After the first action is completed, it will go for the second one, and so on, after it finalizes. And then Python standalone client is different in the way that we log in, we get a plan, and we only get one update of the plan. So we don't do iterative looping of the plan to get the status and so on. And you may find, obviously, in the GitHub repository, the Python script. So we will be doing a couple of demonstrations. We will be doing 2 demonstrations. One is going to be using iShoeRobot, another one is going to be using Summit Excel. So actually, you may follow this tutorial in the GitHub repository. The one that I will be showcasing right now is explained in very much detail under the documentation section in the tutorial section. So we will be consuming object detection NetApp using robot and middleware. So for this demonstration, the material is we are going to need a robot. Since this robot doesn't have a desktop operating system, we will be needing another machine, another laptop. In this case, it's going to have a ROS Indigo Ubuntu 14, which is actually a little bit old, to visualize the camera of the robot. And then there is some sort of server where the middleware is running. This case is running under Ubuntu 18. So first thing first, the middleware is deployed. As we can see, all the modules are running over here. To deploy the middleware, there is a script available. So we will just launch deploy.sh and everything will be configured. Interestingly enough, we have to configure the gateway to actually be exposed to the outside world. So robot is outside entity from the middleware deployed in the machine. So we will do kubectl expose and the gateway, and we will use node port to do this. What is going to happen next is that we can actually try to validate if the robot can reach the middleware by trying to go to the robot, go to web browser and try to put the IP address of the middleware machine, followed by the port that was provided by the node port over here. And we should be able to see also gateway reachable. So now what we are going to happen is we will ask a middleware to deploy a network application for us. In this case, it's going to be object detection. We will be using the Python script, the one that is very easy to use, standalone. We will put in the ID of this task and it will deploy it. Finally, what we need to do is we also have to expose this network application to the outside world, meaning that we have to do kubectl expose and the network application using node port. So we will also expose this one up. Our final configuration should look something like this one in Kubernetes. We have deployed our middleware, the network application is deployed, and we have a node port for gateway and object detection. So the topology of the system of this experiment is looking like this. We have a machine where the middleware is running, and in this machine is where the network application is deployed. Then we have a robot which communicates using ROS with some machine installed ROS Indigo. There is bidirectional communication using ROS master URI. So both have visibility of ROS topic node and ROS topic list and so on. And then between the ROS ecosystem and the middleware, the communication is actually REST. Okay, so now finally, we want to launch Beauty's network application client to be able to communicate with the deployed network application. So the network application is running in the cloud, but it needs some data to be input to do the predictions. So what we will do is we will use this client. In this case, since this robot is using very old ROS distribution, in this case is ROS Indigo, the network application client is bundled using Docker, so we can run it even with Python 3. And the configuration for this one looks like this. We are including the IP address of the network application and the port, and then there is some environment variables we have to configure. Basically, ROS master URI, so the Docker deployed container knows about the robot topics. And then we are also including the input topic, which is the camera of the robot and the iris camera image, and then the output topic we wanted it to be results. So now we may use ROS run image view ROS package to visualize what the robot is actually detecting. Here we have two examples, luggage, bottle of water. I will play video demonstration. So basically what's happening here is we are asking the middleware to deploy the NetApp, and then we are launching the network application client with the topic of a camera. And now we will be able to do the visualization of the predictions. Okay, so now I will go and try to grab the bottle of water away from the robot. So the robot should be able to visualize the suitcase. Now it's detecting suitcase. And now I'm putting back a bottle of water in front of robot. And it is detecting. So we have successfully deployed the network application, a very lightweighted robot, which is actually running Raspberry Pi is actually consuming some very fancy YOLO object detection service, which is very nice. Finally, there is other demonstration under a different environment. Well, it's slightly different, which is using Summit Excel. Actually, there is typo here, should be Summit Excel. Well, the main difference over here is that the middleware is being deployed under Oracle VirtualBox, which means the middleware is running in virtual machine, which is another kind of configuration that we really want to have a look. Obviously, the performance is a little bit not so much better compared to running it on bare metal, but we will be running it anyway. So the only considerations is that for this demonstration to be running smoothly, we will configure network car to use bridge adapter, and then we will be using Arbis inside the robot. Since this robot has Ubuntu desktop installed, we can log into the robot using Remina or other remote desktop program, and we will just launch Arbis for visualization of the results. So the example is very similar to ISOIC. The only thing is in the deployment of the container for the network application client, we don't have to put ROS master URI, since this container is running in the very same machine where the robot is. So using host environment variable, everything is running smoothly and enough. Only thing is we are using input topic, the camera of the robot, which is from BTC camera image raw, and then the output topic is still results. So I will run video. Yes. So we are in Arbis. We are looking at the 3D LiDAR readings from the sensor. And we have included here an image, and then it is connected to the results. Here is my colleague moving around. Summit Excel will detect it, so there is a bounding box around colleague. And yes, network application running on Summit Excel. This is it. Thank you very much for listening. Any questions?
Thank you very much, Adrian. Yes, actually, we have some questions in the chat. But before that, I want to just ask the people in the audience if they have any last-minute questions or they want to. Okay, great. So so 4 questions for you, Adrian. First one is that if someone's robot applications are not containerized, can they still use 5G, the 5G era solution? And then a supplementary question on this question is, can they keep their existing gross software in the robots and at the same time use a feature provided by the 5G era solution?
Mm-hmm. So in terms of second question, the robot does not have to be modified in any kind of way. So your ROS is running the same as usual, but you need to run the action client, action server, or the Python standalone client to be able to request a task to the middleware, which then is it is the way to say from the robot to the middleware, I want to get object detection, I want to get navigation. This is the way. And then for keeping the track of the status of these deployments, if you want to keep the track of each of the deployed containers, then you will use action client, action server to do so. And if not, you will use the Python standalone client. But you don't need to modify your ROS in the robot whatsoever in any way. And then for the first question, I just want to make sure, did you ask, can we use the applications if they are not containerized?
Exactly. Yes.
No. Well, at least with the 5-year middleware, the thing is that we are doing something that is called the onboarding of the network applications. In this process, each of the applications in the library of the 5-year. So imagine there is like a catalog of applications. So you go to Google Store, there is many apps for you to download. This is the same. We will onboard each of the network applications that the robot can potentially use. And this onboarding requires the network application to be Dockerized. However, we will provide in tomorrow demonstration the way to do the onboarding of this network application. And we will have a lot of documentation, so don't be scared of containerizing applications. The thing is that traditional ROS development doesn't take into consideration Dockerizing applications. This is not the traditional way. However, for orchestration of resources, for replicas, it has to be containerized. So this is the way we follow.
Great, thank you very much. Thank you, Adrian. I mean, the explanation is very clear. And talking about easing fears, there is another question is there a more intuitive way from the one demonstrated to onboard the robots, because the template in the GitHub and the Postman are a bit scary for certain people. So they're asking if there's a more intuitive way to onboard the robots.
So currently, you are not required to use Postman. You will be able to use our 5-year dashboard to do so. In the hackathon, you will be able to use our official interface, so you don't have to play around with the Postman, and you don't have to log in and register and so on. But the template pretty much stays the same. What I want to say, however, is not all the information is actually compulsory. So if you don't want to put the weight of the robot, if you don't want to put the maximum payload of the robot, that's absolutely fine. The only difference is that the middleware will not be able to plan with this information, but it's not compulsory.
So if I can just add a small thing, the dashboard will also feature a converter for the files, so that the people can also be more intuitive in the way that they can at least semi-fill the template from there. So yeah, thank you very much, Adrian. And then 2 more questions. One of them is when are we planning to release the software directly as ROS packages?
June.
June. Perfect. So people wait until June, and we should have everything in place. And then, what is the exiting security feature that is going to be used in the middleware, that is currently used?
What is the security features in the middleware?
The exiting security feature.
Exiting.
The existing security features.
Let me think about this one. So we have login with. So we have. I think Bartosz, can you take this?
Oh yes, yes, absolutely. So at the moment in the middleware, we are having the role-based access control that allows, that provides a different access to the vertical users and to the administrators. The administrators are able to provide the actions that are required to incorporate at the multiple middleware instances under the same umbrella, while the vertical users are responsible for creating the plans for the robot, for the execution, adding the new network applications. And then we also have a third category of the robot, which will be able only to request the actions that are actions in the context of operating the resources, like the deployment, the removal, and the switchover that I will cover in just a moment. On top of this, there is a standard token-based access control, so each endpoint of the middleware is secured. And yeah, that's it.
Passwords were encrypted, I think, also in the packet.
Yeah, no, the standard encryption, standard security measures that each application should have.
Okay, thank you very much.
Thank you both. Great. Those were the questions. So, Adrian, again, thank you very much for your interesting presentation. And then we will now move to the last session of day one of our webinar, which is the tackling the issue of offloading of the robot tasks on demand. Adrian will discuss the main challenges and solutions, as well as provide a demonstration on Summit Excel and ISO, as we discussed before. And Bartosz has provided will provide the edge switch over demo, and Guillaume will cover the expectation of the robot developers on 5G, followed by a short Q&A. So Adrian, again, I will give you the word to.
Hello, can you hear me?
Yes, Guillaume.
Yes. Hello, everyone. My name is Guillaume Gary. I am a researcher and developer team of Robotics. We are manufacturers of Summit Excels and any other robots. So we are quite proficient in the ROS developing packages, and we know how hard is to the developers to understand more of the concepts coming from the cloud, and the need that the developers has in order to offload some part of the computational task to an external device, because of several reasons that we exposed in this webinar. One of them is the battery life, and the other one, the ones for at least for our point of view, is one is the one you, even though you have the resources, you will deplete your battery really fast, and the other one is you don't have enough resources to do the task you are required to do it. So one of the challenges that the robot developers has is to offload in an easy way, because the problem is, like, my colleagues are ROS experts, not cloud experts. So they are quite they know much in detail how to perform a task in the robot, but they have little knowledge of to do it in a different machine. Even though without the 5G era, it's quite complicated. We have to do some tricks and dirty stuff in order to make it work in some ways, in order to offload something. And we don't want it to do that. We want something that is easy, as suppose Adrian, as suppose Michel, as suppose Bartosz. Something that we can install it in a machine that some DevOps give us the infrastructure, and offload the things over there and communicate within ROS, because if they have to learn another language, the problem is that at least in our experience is like in the private companies, the developers are few that know ROS, and even though some fields in ROS like navigation, localization, grasping, ARM development. So if we have to ask them to know how to deploy things on the cloud or the edge or on another machine, they will be, at least for a long time, because they are a little bit overloaded, because they have to deliver the packages, they have to deliver the software, the things that they are experts. So 5G era is one of the big opportunity for the ROS developers in order to release this kind of task to the ROS, and focus the efforts of the developers to do what they know how to do the best, is to deploy ROS applications. So with a little bit of knowledge and a little bit of learning, they can make the network applications, and with a DevOps help, they can deploy it outside the robot. So this is one of the big challenges that solves 5G, and with the idea that the robot owner or the robot developer doesn't care where the load is deployed. So as Bartosz said before, you can do it with Kubernetes, but the vanilla Kubernetes. Of course, a lot of companies use vanilla Kubernetes to do a very complex things, but the problem is that they have experts on Kubernetes in order to deploy these things. And the other problems we have is, like as Renji said on the beginning of the talk, we have an unstructured environment. So if we are going to use the robot outside, we will change our communication quality. It will change. So maybe we need to switch from one place to be offloaded to another. So 5G era solve this all these problems and allow us, the ROS developers, to focus on what we do what we do best, is to do ROS applications and to do robotic stuff, robotic software. So for us, it's a big improvement in our workflow. As Adrian will show, and in the videos that we see, that we don't need anymore to make anything in the robot, and we don't need to invest hundreds or hundreds of hours in order to deploy things in the cloud or in the edge. I think that's everything from my side. I'm happy to answer any question you have.
Many thanks, Glenn. That's a very good overview for where are we come from for the robot developers. Do we have any question from Andreas? I think we still have one demo on edge switchover, and then some time for questions. So maybe.
So, sorry, my microphone had an issue. No questions as I see from the chat. So we can move on to the next step. Can you hear me?
We can hear you. I guess
Yes.
the person will do the demonstration on edge switchover.
Yes. So going back to me for a few more seconds, to expand on what Adrian has been saying before, and also what Guillaume has mentioned in terms of the interoperability and the communication between the multiple middleware instances and their cooperation, we are implementing a functionality called edge switchover. So let's assume the scenario in which one robot is utilizing two middlewares at once, and it is conducting the work, and at some point, one middleware is not responding. There is a power outage, the data center is not available anymore. Let's assume this situation. So what will happen then? This is why we have a security measures to prevent such a situation and to allow the robots to continue their work. Sorry. Okay, so as the main purpose is, as I just said, to increase the system resiliency and the availability. Also, by using the edge switchover, we are aiming to better optimize the resource utilization and to provide the better quality of the service and the quality of experience to the robotic applications. And also, as a main point, it is our way to communicate between the multiple middleware instances to achieve the same goal. So how it works? Essentially, the scenario that I have described just a moment before is expressed under this picture. Let's now assume that middleware while working with, the robot while working with the middleware 1, 2, and possibly 3, just loses the connectivity to the middleware 1. So what will happen is the robot, when it sees that there is no connection to the middleware 1, can request the middleware 2 or middleware 3 to take over the work that has been done, that was being done by the middleware 1. Or what it can do, it can ask directly middleware 1 to switch its own resources to the other middleware because it knows that the middleware 2 provides the better latency for it. That is crucial for conducting a task that is doing at the moment. And how it works? We are moving all the resources that the robot uses from the middleware 1 to the middleware 2 or to the middleware 3 to actually enable the best possible usage of those resources. When the request like this is made, we are we're calling the middleware to delete the existing resource and to continue their work with the same resources in the middleware 2 or in middleware 3. And by this, we are fully utilizing the middleware as a distributed system. To showcase how it works, I'm going to show you the short video to explain what you're seeing in here. In the terminal on the left-hand side, you can see the local middleware that is running on some local edge or private cloud. And then on the right-hand side, you can see the contents of the middleware that is running on the public AWS cloud. So what we are going to do in here is we will initiate the call to the middleware on the left-hand side to switch to the middleware running in AWS. And now, as you can see, the resources, the NetApp that was running, the network application that was running in the local middleware has been moved to the middleware running in the cloud. And now the robot knows that it can continue to work with the same network application, just under the different address. Okay, and that's it. Thank you very much.
Perfect. Thank you very much. Thank you, Bartosz. So this basically concludes our day today. But before closing the day, I would like to also just note a few things about our project. So as has been mentioned before, and of course you can find many more information on our webpage, 5G era will also deal with 4 use cases. Our first use case, the first use case we're going to tackle and has already been discussed is concerns public protection and disaster relief, PPDR for short, where we will be designing a new network application for an enhanced autonomous service in unstructured environments. And we aim to demonstrate solutions that would serve as technological, let's say, avenues between standard communication solutions and the legacy ones already existing. And we also aim to demonstrate very a seamless integration between edges and mobile operations. Then we have a use case that deals with 5G enhanced semi-autonomous transport that is part of our partner led by Bring Auto, which we aim to demonstrate how network applications can improve the experimental facility and how we can use lightweight unit virtualization techniques to build the moving app-based environment for the environment to help with reduced service creation in the transport domain. And robots in this use case will be able to work in teleoperated and semi-autonomous modes, relying on 5G technology. And this is part of the designing of new network applications in the sector of semi-autonomous transport. Then our third use case deals with enhanced healthcare robots, which we will deliver. We will basically deliver quality of service to map several data streams coming from sensors, coming from video streaming, and integrating alerts, and demonstrates the security aspect of network applications endpoints, and how the data streams are able to preserve sensitive and confidential data. And of course, given the recent COVID-19 pandemic, we consider this a very important, a very strong use case for our project. And we want to demonstrate how these robots can carry supporting materials for this pandemic and future pandemics. So how this utility can actually benefit healthcare workers that depend, and that their job becomes way more efficient and less dangerous by supporting this autonomy on behalf of them. And of course, the new network application will be designed to tackle the emerging field of 5G enhanced healthcare. And finally, the fourth use case of our project is the use case to enable an interface between the ROS, between ROS1 and an industrial production cell. So how can our solutions benefit 5G remote enabled assistance for various manufacturing processes that are part of the widely discussed field of Industry 4.0, and how deploying such a solution in a very highly flexible and robust manufacturing environment with large-scale fabricators using a bracing cell with our partners, the related partners for this use case. And of course, we will need these robots to be able to tackle the two use cases, being, let's say, checking that the robots are outputting whatever they're being designed for, and that the robot itself infers a desired output from a human perspective, so they're from the human input point of view. So with that, these are the four use cases. I don't know, Remshi, if you want to add something on top of what was discussed.
I think it's a very good summary from Andreas, and we hope every software we build up will be translated into more convenient ecosystem, better development environment for robot developer, and also give a better reach of current telecommunication solutions testbed to the robot community. So that's our ultimate goal by doing everything we showed you today. And we are kind of paving the way on distributed robotic systems. In the morning, we show how to do our network applications. In the afternoon, we show the middleware. Tomorrow, we will show you some of the 5G testbed to be used in the project. And probably this is, another perspective, another spectrum of the project. And it's good chance for you to ask questions about the testbed. And then we will give you some tutorials on how do you do it yourself, because eventually you are the ultimate customer for us, the end user for us, the developer of the network applications. I want you to use 5G approach, build your application, and then eventually to deliver things, get better deployment of the robot, which we can't do at the moment. That is the ultimate goal. I'm looking forward to see you tomorrow in the tutorial, and see you in the future in our events.
Great. Thank you very much, Remshi. Thank you very much, everyone, for joining. And as I said, we couldn't put it better. We will look forward to seeing you tomorrow and in our future events. Yeah, right. Thank you to the speakers of today's speakers as well for their presentations. And
that's the end of our